Hello. All right, I'm going to tell you something and ask you just to go with it. Okay. This is called, so when we've been writing complex numbers in polar form, we've been writing them like this: r times cosine theta plus I sine theta, right? And I'm going to write something. This is Euler's formula. Euler was a mathematician. And to derive it in any really helpful way, you kind of need calculus. Okay, so stay tuned for next year if you take calculus. For now, I'm just going to ask you to go with this. This is equal to r e to the I theta. So basically, we're replacing this, the shortcut cis, right? Cosine of theta plus I sine theta, that is the same as e to the I theta. Is that intuitive? It is not. Is there an easy way for me to explain why that's true? Not right now. Okay, so let's just go with this because it's going to make our life a lot easier to think about, to use this form of this polar form of a complex number. Okay, so we're going to go with this form for now, because if we have this form, what if we have two complex numbers like z1 equals r cosine theta plus I sine theta, and we'll sine theta 1. And we have another one, z2 equals, I guess that's r1, r2 times cosine theta 2 plus I sine theta 2. We just have two complex numbers in polar form. Sorry. What if we want to multiply them together? Well, let's think about this in using Euler's formula in this form. We could just write this as r1 e to the I theta 1. And we could write that z2 equals r2 e I to the theta 2. Right? And now if we want to multiply these together, z1 times z2, you can see how much easier it's going to be to multiply these two things together compared to these two things together, which we'd have to multiply things out and use different identities. Let's just multiply these together. We have r1 e to the I theta 1 times r2 e to the I theta 2. And we just use our properties of exponents, which we've all got ready, right? And this is just going to be, okay, r1, r2, e to the I theta 1 plus I theta 2, which we could just write like that. So we just multiply the two r's together and add the two thetas together. If we wanted to put it back into polar form like we're used to, we could just write this as r1 times r2, and then cosine theta 1 plus theta 2, plus I sine theta 1 plus theta 2. Right? I mean, if you use this E form, use Euler's formula, you don't really even have to remember anything, right? It just comes from the properties of exponents. If you're using this form, you kind of do have to remember things. I mean, this doesn't at all seem intuitive to me that it's going to be r1 times r2, and then these two angles added together if I use this original form. Okay, so I find this like so much easier to use for these properties. What if we had a quotient, right? If we had z1 divided by z2, well, we'll have r1 e to the I theta 1 over r2 e to the I theta 2. We can just write that as r1 over r2 e to the I theta 1 minus theta 2. All right, just from the properties of exponents. If that's not clear to you, maybe just take a minute and write things out, make sure that you understand where that comes from. And okay, so if we wanted to convert this back, whoops, that's an r, we could write this as cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. But again, I mean, this isn't intuitive to me to remember. Using these this form, I don't even have to remember anything. I can just easily derive it from like one step properties of exponents. Okay. What if, so let's I guess do some examples here. So find the product of z1 times z2, and they give us these two equations, these two complex numbers. So I'm going to write z1 in Euler's form. Whoops, e to the I times 80 degrees. And z2 is equal to r times e to the I times 145 degrees. Okay, so, oh wait, this is 4, and this is 2. So z1 times z2 is just 4 e to the I 80 times 2 e to the I 145, which is 8 e to the I times, add these together, 125 degrees. So it's going to be 8, and we could just write cis 145. That means cosine 145 plus I sine 145. Oh, wait. Look, you're like, where did 145 come from? I have to add them together, obviously. This isn't 145 plus 80 is not 125. It is 225. And this is 225. Although actually this is a good point. I've been a little bit sloppy. Before you can put things in this form, honestly, you really shouldn't have it in degree form. You really should transform it to radians. Okay, so let's do that. Let's not be sloppy here. Let's redo this in the proper way. So I'm going to rewrite this. So 80 degrees. Well, we could just transform it here. We could write this as 8 times cis of, so 225 degrees, let's think is 180 plus 45. So that's going to be 5 pi fourths, which I guess is what they have there. And if we wanted to keep going, this will be cosine of 5 pi fourths plus I sine of 5 pi fourths. And we can evaluate these, right? Cosine of 5 pi fourths, like they say, is negative square root of 2 over 2. And sine of 5 pi fourths is negative square root of 2 over 2 as well. So if we multiply this out, we'll have negative 4 times square root of 2 minus 4i square root of 2. Is it easier to put it into this form and then bring it back into cosine and I, or cosine and sine? I don't know if it makes this problem easier, but it makes the derivation or knowing what to do easier. Does that make sense? Okay, so let's try another one. With quotients, find the quotient of these two numbers. So z1 divided by z2. We could write this as 2 e to the, let's just write it as 213i divided by 2 e to the 33i. Oh wait, sorry, 4. It's 4. This is going to be 1/2 e, so 213 minus 33 is 180, right? Is that true? Let's get this right this time. Yes. E to the 180i. So I could write that as 1/2 cosine of 180 plus I sine of 180. All right, well, cosine of 180 degrees is -1. And sine of 180 degrees is 0. So this is just going to be negative 1/2. Is that true? Yes. Okay, so moral of the story here, if you wanted to jump from here to here, you can. It's just when it's a quotient, it's just the top angle minus the bottom angle.